So lecture 19 goes over solving systems of equations, and we're going to look at linear systems where the equations are linear equations, and then nonlinear as well, and then we're going to apply it to word problems. All right, so a system of equation is basically a collection of two or more equations, each one containing one or more variables. So for example, you could have 2x plus 3y equals 5, and then x minus y equals 10, for example. So you have the two variables, x and y, and then the two equations. And basically, to solve it, you need to find the solution, and the solution is all the values of the variables that satisfy simultaneously each equation in the system. So to solve a system means to find all the solutions of the system. If a system has at least one solution, we call it consistent, and you'll see that there are systems that have no solutions, and those are called inconsistent. All right, so first of all, we're going to look at systems, linear systems, and basically they have this form: a1x plus b1y equals c1, a2x plus b2y equals c2. And the solution of the system is all the points xy that satisfies both the first and the second equation. So we say that it satisfies the system. To solve a system, again, means to find all the pairs xy that satisfy all the equations, and we have basically three methods. We can solve a system by graphing, by substitution, and then by elimination. So if you want to solve a system by graphing, we're basically going to graph the two lines, and then if the lines intersect, the intersection point is going to be the solution. Okay? So you could have the case where the lines, so if you have one line and then another line, so the solution is going to be this point right here. Or, and in that case we call the equations independent. Or we can have that the lines coincide. When the lines coincide, we can have one line, and then when you graph the second line of the system, it just overlaps. So the lines are basically the same, and they basically intersect at infinitely many points. So we call that system dependent. Every point on one of the lines, which is the same, is going to be a solution point. And then the third case is when the lines are parallel, and when the lines are parallel, well, they don't intersect anywhere, right? So there is no solution, and we call the system inconsistent, no solutions. So for example, to solve these three systems, we would basically graph each line. So graph this line and graph that line. So let's do that. So remember, to graph, I'll need 2 points. So when x is 0, y is going to be 2. So 0, 2. And then when y is 0, x is 4. So then the first line is this one. This is the first line. And then you graph the second line. When x is 0, y is -1. And then when y is 0, x is 1. So this will be the second line. And then you can kind of see the intersection point, but the intersection point is basically where these two are equal to each other. So I can, let's just do it. So if I solve for y in the first one, I'll have 2y equals negative x plus 4. So y equals negative 1/2 x plus 2. And then if I solve for y in the second one, I'll get that y equals x minus 1. So I set them equal to each other. Negative 1/2 x plus 2 equals x minus 1. I subtract 1x, so negative 3/2 x equals negative 3. Multiply by 2. I'll get negative 3x equals negative 6, so x equals 2. So when x equals 2, y will be, we can use this one. Y would be 2 minus 1, so y equals 1. So the intersection point is 2, 1, which is kind of what I suspected, but so this is the intersection point, 2, 1. We pretty much never use the graphing one. We use substitution or elimination. So if you want it, you can also graph these two lines and see if they intersect or not. If you graph them and they look the same, that means that they're infinitely many. And if you graph them and if they're parallel, then that means there's no solution. Alright, so let's see the next one. So to solve by substitution, we're basically going to solve for one of the variables in an equation in terms of the other. So what do we mean? If you look at this system, you see I can solve easily for x in the first equation. So I'll get that x equals, add 2y to both sides, 2y plus 1. So then I'll substitute, instead of x, I'm going to put 2y plus 1 in the second one. Okay? So now I'm going to do 4 instead of x. I'm going to do 2y plus 1. And then minus 3y equals negative 1. And then you notice in this one, you are down to one variable. So you can solve for y in here. So let's solve for y in here. So I'll have 8y plus 4 minus 3y equals negative 1. Which gives me 5y equals negative 5. And therefore y is negative 1. And now I go back to my substitution to get x. So x now is going to be 2 times y, but y is negative 1 plus 1. So that will give me that x equals negative 2 plus 1, negative 1. So the solution is the ordered pair negative 1, negative 1. So this is what we mean by back substitute. Substitute the y you solved for back into your equation. And you can check your solution in each equation. So if you substitute negative 1 for x and negative 1 for y, you're going to get true statement for the first and for the second. The other method is called the method of elimination. And basically we're going to rewrite the equations. We're going to multiply both sides of the first, or both sides of the first and both sides of the second, by such numbers, such that when we add or subtract the two equations, one of the variable goes away. We eliminate one of the variable. So if you look at the system, for x I have 3x and 5x. So if I was to add these two equations, I would get 8x. So the x would not go away. But if you notice the y, if I add 2y and then the negative 2y, the y goes away. So basically the system is already set up for elimination. So we're going to add both equations. So I'm going to add the left side. So it'll be 3x plus 2y plus 5x minus 2y equals 4 plus 8. So I'll get 8x notice that the y goes away, it's eliminated, plus equals 12. So then x equals 12 over 8, which gives me that x equals, if I divide by 4, I'll get 3/2. So this is my x, but remember, to solve a system, it means to get the order pair xy. So I need to get y now. So I'm going to use this in one of the equations. So I'm going to do 3 instead of x. I'm going to put 3/2 plus 2y equals 4. So this will give me 9/2 plus 2y equals 4. Let's multiply by 2. And get 9 plus 4y equals 8. What just happened? Anyway, 9 plus 4y this was 9 over 2. I multiplied by 2, so 9 plus 4y equals 8. Therefore 4y equals -1, so y equals -1/4. Alright, so x equals 3/2 and y equals -1/4. Therefore the solution is the point 3/2, -1/4. Alright, so now let's solve this system by elimination. So first decide which variable you want to eliminate. So we eliminated y in the first system. Let's eliminate x. So we're going to look at x. X is over 2 in here and the -6x. So what do I need to multiply x over 2 to get 6x out? Because if I have 6x and I add it to -6x, I eliminate x. So, well, I need to multiply by 12, right? Because 12 times x over 2 is going to give me 6x. But make sure you multiply everything. Okay, so now I multiply 12 by x over 2, it gives me 6x. 12 times -2y over 3 is going to give me -8y, and then equals -24, -2 times 12. And then I leave the second equation the same. And now notice that when I add the two equations, the x is going to go away. So add is going to give me 6x minus 6x minus 8y plus 8y equals -24 plus 24. Well, in the process of eliminating x, you notice that we eliminated y as well. So basically what we reached was 0 equals 0. Okay. This is the case where there are infinitely many solutions. So we have infinitely many solutions. Basically, the lines are the same. Lines are the same. So how do we write this? The solution is all the pairs x, y such that you just pick one of the equations. I can pick the second one, such that -x plus 8y equals 24. Okay, so this is the solution, and this is how we write it. All the points that are on one of the lines, because if you are on this line, you are on the other line, because the lines are the same. All right, so let's move on to systems of nonlinear equations. So basically, it could be that the equations are not lines. When you graph them, they're not lines. We know that the first one, y equals x squared plus 1, is basically a parabola with moved up one, right? So it will be like this. And then the line y equals x plus 1, when x is 0, y is 1. When x is 0, y is 1. And then when y is 0, x is negative 1. So then I'll have this line. All right. And you notice that the intersection points are going to be basically this point and then this point. I drew my parabola wrong. Let's see, what is the value when x is 1 for the parabola? I would get y equals 1 squared plus 1, y equals 2. So the point 1, 2 should be right here. So the solution are the 2 points of intersection, the point 0, 1, and then the point 1, 2. Okay, so it's this point and then that point. Now let's solve this nonlinear system of equation. We know that the equation x squared plus y squared equals 25 is a circle centered at the origin and the radius equals 5. And then the second equation is just a line. So let's solve for y in the line. So I would have that y equals 2x plus 5. And let's do this one by substitution. So I'm going to substitute, instead of y in the first, I'm going to put 2x plus 5. So this will give me x squared plus, instead of y, I'll put 2x plus 5 squared equals 25. And then I calculate this. This is 4x squared plus, this should be minus 5, sorry. It's 2x minus 5. It'll be 4x squared minus 20x plus 25 equals 25. The 25 goes away. X squared plus 4x squared gives me 5x squared minus 20x equals 0. And then if I factor this, I'll have 5x times x minus 4 equals 0, which gives me that x equals 0 and x equals 4. But now x equals 0 substituted in here gives me that y equals 2 times 0 minus 5, which is y equals negative 5. And x equals 4 substituted in here again will give me that y equals 2 times 4 minus 5, which is y equals 8 minus 5, 3. So the solutions are the points 0, negative 5, and 4, 8 minus 5 is 3, not positive 3. 0, 3. 4, 3, sorry. So we can plot these points. 0, negative 5 is here, and then the point 4, 3. 4 for x, 3 for y. Well, it has to be on the circle, so it will be here. So this is the line. 4, 3, the point is 0, -5. There you go. We solved a system of nonlinear equations. All right, let's solve another system of nonlinear equations. Again, we know that square root of x is going to be looking like this. When x is 0, y is 0. When x is 1, y is 1. When x is 4, y is 2. So we know this is square root of x. And then we can graph the line y equals, so when x is 0, I would get that y equals 2. So the point 0, 2. And then when y is 0, x equals 2 as well. So I'll have the point 2, 0. So the line would basically be this, and the intersection point looks like it's at 1, 1. Let's verify it algebraically. So algebraically, we're gonna substitute y as square root of x. So instead of y, I'm gonna put square root of x. So I'll have y equals 2 minus x, but y is square root of x. So I have square root of x equals 2 minus x. And remember how to solve this. We square both sides. And square root of x squared is x. And then I have 4 minus 4x plus x squared. So then x squared minus 4x plus 4 equals x. Subtract x, I'll get x squared minus 5x plus 4 equals 0. So I have x minus 1, x minus 4 equals 0. Yeah, so then x equals 1 and x equals 4. When x equals 1, y would be, well, we know that y is square root of x. So y would be square root of 1, which gives you that y is 1. And when x equals 4, y would be square root of 4, which y would be equal to 2. So our candidates are x equals 1, y equals 1, and x equals 4, y equals 2. And remember, when we solve radical equations and we square both sides, we might introduce extraneous solutions. So that's why we have to check our solutions this time. So check 1, 1. So is it true that 1 equals square root of 1 and then that 1 equals 2 minus 1? Yes. So 1, 1 works. And then check 4, 2. So is it true that 2 equals square root of 4? Yes. Is it true that 2 for y equals 2 minus 4? No, 2 does not equal -2. So then this one doesn't work. So the only solution is the one that we got graphically, 1, 1. All right, so in the next video, we'll look at applications.